Earth has not always been as warm and stable as it is today. At certain times, large sheets of ice covered wide areas of land, lowered sea levels, and changed the shape of continents. This period, called the Ice Age, was not a single event, but a series of cold and warmer phases that lasted for hundreds of thousands of years. During these conditions, living things adjusted to survive. Large animals with thick fur lived in cold regions, and early humans developed ways to find food, make tools, and protect themselves from the cold. So, how did climate changes affect life and shape the present-day environment? The quiet beginning of the Ice Age unfolded through slow and steady changes that were almost impossible to notice at first. There was no sudden drop in temperature and no clear moment when life on Earth shifted from one state to another. The change developed over very long periods of time, shaped by small differences in climate that gradually added up. The Earth continued to turn, the oceans continued to move, and the land remained in place, yet the balance of heat and cold was slowly adjusting. At the start of this long process, the planet still supported wide forests, open grasslands, and large bodies of water that followed familiar patterns. Rain fell in regular cycles, and rivers carried water across the land, as they had done for a very long time. Animals moved through their environments, feeding, migrating, and reproducing, without any clear sign that the conditions around them were beginning to shift. The air did not feel dramatically colder, but over time, small differences began to appear. Winters started to last a little longer than before. Cold periods extended slightly, while warmer seasons became less intense. In many regions, snow that once melted quickly began to remain on the ground for longer stretches. At first, this change was slight. A thin layer of snow would stay for a few extra days or weeks. Then, over many cycles of seasons, some areas began to hold on to snow even when warmer weather returned. This gradual persistence of snow marked an important stage in the changing climate. Snow has the ability to reflect a large amount of sunlight back into space. When more snow remains on the ground, less heat is absorbed by the Earth's surface. This leads to cooler conditions, which then allow even more snow to remain. Over long periods of time, this process strengthened itself. Each season added a small amount to the overall cooling, making it easier for snow and ice to survive through warmer periods. In higher regions such as mountain ranges, these changes became more noticeable earlier than in lower areas. Snow began to accumulate year after year, forming thick layers that did not fully melt. As more snow piled up, the weight of the upper layers pressed down on the layers below. This pressure caused the lower layers to become denser and more compact, gradually turning into solid ice. This transformation did not happen quickly. It took many repeated cycles of snowfall and compression. As the ice thickened, it began to move very slowly under its own weight. This movement was not fast or sudden. It occurred at a steady pace, with the ice spreading outward from the areas where it had built up the most. These early ice masses marked the beginning of glaciers. They formed in regions where the conditions allowed snow to survive through many seasons without fully melting. Over time, these glaciers grew larger and extended further into surrounding areas. The presence of growing ice affected the land in several ways. The surface beneath the ice experienced pressure from the weight above. Rocks and soil were gradually shaped by this slow movement. At the same time, colder temperatures influenced the types of plants that could survive. Some plant species that required warmer conditions began to decline in certain regions, while others that could tolerate colder environments became more common. Oceans also played an important role in this gradual shift. Water temperatures began to decrease in certain areas, affecting currents that moved heat around the planet. These currents are part of a large system that distributes warmth from one region to another. When their patterns changed, even slightly, it influenced weather conditions across wide areas. Some regions received less warmth than before, which contributed further to the cooling trend. The atmosphere also changed during this period. The balance of gases that trap heat, including carbon dioxide, shifted over long periods of time. Lower levels of these gases allowed more heat to escape into space. This contributed to the overall cooling effect. The changes in the atmosphere were not sudden. They developed gradually, influenced by natural processes such as the movement of continents, volcanic activity, and interactions between the oceans and the air. The position and movement of the continents also affected the climate. Land masses slowly shifted over millions of years, changing the arrangement of oceans and altering the paths of currents and winds. When continents moved into positions that allowed ice to form more easily near the poles, it became easier for long-lasting ice sheets to develop. These shifts in geography helped create conditions that supported the growth of ice over large areas. In polar regions, snow and ice began to build up more steadily. These areas receive less direct sunlight compared to other parts of the Earth. As a result, they are more sensitive to cooling. Once ice started to accumulate, it was more likely to remain in place. Over time, the ice in these regions grew thicker and spread outward. This expansion did not happen quickly, but it continued as long as the conditions supported it. The cooling trend also affected rainfall patterns. Some regions became drier, while others experienced changes in the timing and amount of precipitation. These changes influenced the availability of water for plants and animals. In areas where conditions became colder and drier, vegetation changed gradually. Forests in some regions gave way to open landscapes with plants that could survive in cooler and less stable conditions. Animals responded to these changes in different ways. Some species adjusted by altering their behavior, such as changing migration patterns or shifting their feeding habits. Others moved to areas where the conditions remained suitable for their survival. Over time, some species declined in number or disappeared from certain regions, while others became more widespread. The development of ice sheets and glaciers had a direct effect on sea levels. As more water became stored in ice on land, the amount of water in the oceans decreased slightly. This led to a gradual lowering of sea levels. Coastlines shifted as a result, exposing areas that were previously covered by water. These exposed regions sometimes became pathways for animals to move between land masses. The slow growth of ice also influenced wind patterns. Differences in temperature between regions can affect the movement of air. As colder areas expanded, the contrast between cold and warm regions changed. This influenced the direction and strength of winds, which in turn affected weather systems. Over time, these changes contributed to the overall transformation of the global climate. The beginning of the Ice Age was not defined by a single cause. It resulted from the interaction of many factors working together over long periods of time. Changes in the Earth's orbit and tilt affected how sunlight was distributed across the planet. These changes occurred in cycles that lasted for tens of thousands of years. When these cycles aligned in certain ways, they reduced the amount of sunlight reaching higher latitudes during certain seasons, making it easier for ice to grow. The tilt of the Earth influences how much sunlight different regions receive at different times of the year. When the tilt changes slightly, it can alter the balance between seasons. Cooler summers in higher latitudes mean that snow from the previous winter is less likely to melt completely. This allows ice to accumulate over time. The shape of the Earth's orbit around the Sun also changes slightly, affecting the distance between the Earth and the Sun during different parts of the year. These variations influence the amount of energy the Earth receives. Over very long periods, these orbital changes combined with other factors to support the gradual growth of ice. The process remained slow and steady, without sudden shifts. Each year added small changes that built upon previous ones. The effects were not uniform across the planet. Some regions experienced more noticeable cooling earlier than others, depending on their location and environmental conditions. Earth slowly slipped into a frozen world through a series of subtle changes that occurred over immense stretches of time. These changes were gradual, building quietly without sudden upheavals or sharp transitions. The planet, which had previously maintained long periods of relative warmth, began to experience small shifts in temperature, in the circulation of the atmosphere, and in the movements of the oceans. Each shift was slight and almost imperceptible at the time, but together they created conditions that steadily transformed the environment. The balance of energy reaching the planet played a central role in this process. The sun's output did not remain constant over millions of years. Slight fluctuations occurred, sometimes lasting for thousands of years, which changed the amount of heat Earth received. These small variations could influence global temperature patterns, affecting seasonal cycles and the long-term stability of climates. Alongside changes in solar output, the composition of the atmosphere also shifted. Levels of gases that trap heat, such as carbon dioxide and methane, slowly declined. These greenhouse gases had once held warmth close to the surface, moderating the temperature across the globe. As their concentrations fell, less heat was retained, allowing temperatures to drift lower. This decline did not happen in a single instant, but progressed over long periods, altering weather patterns and the thermal behavior of oceans and land. Oceans responded to these shifts in complex ways. As surface temperatures fell, seawater cooled and began to change its circulation patterns. Cold water became denser and sank in certain regions, pushing warmer water to the surface in other areas. These movements redistributed heat around the globe in a manner that reinforced cooling trends. Ocean currents that had once moderated the climate began to slow and shift, creating regions where water stayed cold for long periods, further encouraging the development of ice in higher latitudes. Ice itself played a role in increasing the cold. Even a small amount of frozen water on land or in the sea reflected more sunlight away from the surface than liquid water or soil could. This reflection reduced the absorption of heat, which allowed temperatures to fall further. New ice formed more easily as conditions cooled, which in turn reflected even more sunlight. Over thousands of years, this feedback between ice and temperature gradually extended frozen areas across the continents and seas. Continental positions also contributed to the cooling. The arrangement of land masses affected how ocean currents moved and how air circulated. When continents shifted or clustered closer to the poles, they allowed polar regions to retain more ice. Large land masses near high latitudes created conditions where ice sheets could grow without melting during warmer periods. Mountain ranges influenced wind patterns and precipitation, guiding snow and rain into areas that could maintain ice over long periods. Volcanic activity had an impact as well. Eruptions released gases and particles into the atmosphere that could block sunlight temporarily, cooling the surface. While individual eruptions caused only brief drops in temperature, a sustained period of increased volcanic activity could have a more lasting influence. Volcanic carbon dioxide emissions also changed over time, sometimes balancing the cooling effects and sometimes amplifying them if emissions were low for extended periods. The slow reduction in solar radiation, falling greenhouse gas concentrations, altered ocean currents, the expansion of ice, shifting continents, and volcanic influence combined in a way that produced persistent cooling. Each factor on its own might not have been sufficient to cause a major transformation, but together they slowly built conditions that favored the spread of ice. Ice sheets began to advance from polar regions toward lower latitudes, sometimes reaching areas that had previously been temperate or even warm. Glaciers advanced across land, reshaping landscapes over thousands of years. As ice moved, it scraped away soil and rock, carving valleys, fjords, and basins. Rivers were rerouted, lakes formed and drained, and sediment was deposited in new locations. This physical transformation reinforced the environmental changes, creating surfaces that retained cold more effectively and slowing the ability of regions to warm even during summer months. In the oceans, floating ice expanded over larger areas, altering the habitats of marine life. Seasonal cycles of freezing and melting grew longer, and regions that once remained ice-free throughout the year became covered in sheets of ice for months at a time. The formation of sea ice also affected the salinity of the oceans. As fresh water froze, salt was left behind in the water, increasing density in some areas and further influencing ocean currents. These changes in water movement reinforced patterns of cooling and encouraged the continuation of icy conditions. Ecosystems adjusted to the colder environment over long periods. Plants and animals that had thrived in warmer climates gradually disappeared from areas where ice advanced or where temperatures became too low to support them. Species that could tolerate the cold expanded their ranges, while those unable to adapt faced decline. These ecological shifts contributed to the overall sense of a world increasingly dominated by cold, reinforcing patterns of growth for ice and long-term climate change. Throughout these processes, the atmosphere continued to fluctuate in composition and circulation. Winds carried cold air from polar regions toward lower latitudes, and storms transported moisture into areas that could support ice growth. Precipitation patterns changed as cold air held less water vapor, which influenced snowfall in regions where ice sheets were expanding. Over centuries, these gradual atmospheric shifts contributed to the overall increase in frozen surfaces across the planet. Sea levels were affected as well. As ice sheets grew, more water was trapped on land, causing ocean levels to fall. Lower sea levels exposed continental shelves and altered coastlines, influencing where ocean currents could flow. These changes in geography and water distribution reinforced patterns of cooling. Even small changes in orbital patterns contributed. The tilt of Earth's axis, the shape of its orbit around the Sun, and the orientation of its axis all shifted slowly over tens of thousands of years. These shifts affected the distribution of sunlight across seasons and latitudes, sometimes reducing summer warmth in regions that had previously melted ice. When summers became cooler, ice from previous winters did not completely melt, allowing it to accumulate over long periods. Ice sheets in some areas grew to thicknesses of several kilometers. Their weight pressed down on the land, causing slow deformation of the Earth's crust. This process influenced the movement of rivers and lakes and altered regional drainage patterns. The growth and retreat of these massive ice sheets over thousands of years created cycles of cold and slightly warmer intervals, each cycle leaving behind traces in the landscape and sediments that recorded the gradual shift toward a frozen world. Temperatures across the globe continued to decline slowly. Polar regions remained cold year-round, and mid-latitude regions experienced increasingly long winters. Seasonal transitions became less pronounced, as the cold of winter lingered and summers failed to provide sufficient warmth to reverse the spread of ice. Areas that had once supported forests and grasslands saw a reduction in vegetation, while tundra and other cold-adapted ecosystems expanded. The slow cooling had an effect on freshwater systems. Lakes and rivers in higher latitudes froze for longer periods, and ice-covered surfaces persisted into months that had previously been warm enough for liquid water. This influenced the life cycles of aquatic species and altered sedimentation patterns, which in turn affected the composition of soils and the development of permafrost in some regions. Atmospheric circulation continued to interact with the expanding ice sheets. Cold, dense air from ice-covered regions flowed outward, influencing wind patterns over continents and oceans. Storm tracks shifted as a result, and precipitation tended to fall in ways that supported the maintenance and growth of ice. Over time, these patterns reinforced the trend toward a colder climate, creating a feedback loop that extended ice coverage. Volcanic eruptions continued to punctuate this slow change, injecting dust and gases into the atmosphere. Short-term cooling events occurred, but the long-term effect depended on the frequency and scale of eruptions. When volcanic activity was high for extended periods, sunlight reaching the surface decreased, supporting the ongoing spread of ice. Conversely, periods of reduced volcanic activity allowed slight warming, but this warming did not halt the overall trend toward greater cold. Throughout these processes, ice sheets moved, sea ice expanded, and glaciers advanced. The physical landscape changed continuously, shaping river valleys, coastal areas, and mountain slopes. Each advance of ice reshaped ecosystems, displaced species, and influenced the global climate system. These interactions were slow and incremental, occurring over thousands and tens of thousands of years, but their cumulative effect gradually produced a world where frozen regions covered much larger areas than they had previously. Over millions of years, the combined influence of solar fluctuations, atmospheric composition, ocean currents, ice growth, continental positions, volcanic activity, and orbital changes maintained a steady trend toward colder conditions. While there were temporary periods of relative warmth, these were brief compared to the persistent cooling that characterized the majority of this era. Each factor interacted with others, creating a dynamic system in which small changes reinforced each other, and no single cause dominated the overall transformation. Glacial landscapes recorded these changes in the form of moraines, drumlins, and other features left behind as ice advanced and retreated. Sediment cores from oceans revealed layers of frozen and colder periods, capturing evidence of changing temperatures, ice growth, and shifts in ocean chemistry. These geological records demonstrated how persistent and gradual the process was, showing a world that transitioned slowly from warmer conditions to one increasingly shaped by ice. Life continued to adapt to the changing conditions. Species of plants and animals that could survive in cold environments spread into regions where ice sheets and glaciers advanced. Those that could not adapt retreated or disappeared from certain areas. Ecosystems gradually reorganized to accommodate new climate realities, creating a pattern of life that was increasingly dominated by species tolerant of colder temperatures. The hydrological cycle adjusted to the new climate as well. Evaporation rates decreased in cooler regions, precipitation patterns shifted, and rivers carried less water during long winters. Lakes in higher latitudes often froze completely, altering habitats for freshwater species. These changes in water availability influenced both terrestrial and aquatic life, further contributing to the establishment of a colder global environment. The cooling affected soil formation and vegetation patterns. In areas where ice covered the land for long periods, soils were stripped away or compacted by ice movement. Vegetation zones shifted toward species that could endure harsh winters and short growing seasons. Over thousands of years, this led to the development of tundra and steppe regions in mid-latitudes, while temperate forests receded to smaller areas or were replaced entirely by cold-adapted plants. In addition, the accumulation of ice on land influenced the gravitational distribution of water. Large ice sheets drew water from oceans, causing sea levels to fall. Lower sea levels exposed continental shelves, creating land bridges between regions and altering the geography of coastlines. These changes influenced ocean currents and weather patterns, reinforcing the spread of cold conditions. As ice sheets expanded, they created high-pressure zones over cold regions, affecting wind patterns and storm systems. Winds carried cold air toward lower latitudes, contributing to the cooling of regions far from the poles. Storm tracks shifted, precipitation patterns changed, and areas that had once received abundant rainfall experienced drier and colder conditions, further reinforcing the dominance of ice and snow in these regions. The slow cooling also affected the chemical composition of the oceans. Cold temperatures increased the solubility of certain gases, altered the distribution of nutrients, and affected the behavior of marine ecosystems. Sea ice formation changed salinity patterns, which influenced ocean circulation and reinforced regional cooling trends. Marine life had to adapt to these changing conditions, with species migrating, evolving, or declining in response to the increasingly frozen environment. The ongoing decline in greenhouse gas concentrations allowed less heat to be retained in the atmosphere, amplifying the effect of the cooling trends. Carbon dioxide and methane levels fell gradually over millions of years, reducing the greenhouse effect and making it easier for ice to persist in polar and high-latitude regions. This slow decline, combined with other factors, contributed to the long-term stability of cold conditions. Glacial and interglacial cycles began to emerge, with periods of relative ice retreat followed by renewed growth. These cycles were influenced by variations in Earth's orbit, axial tilt, and precession. Each cycle left behind physical evidence in the form of ice sheets, glacial deposits, and changes in sea level. While temporary warm periods occurred, they were insufficient to reverse the overall trend toward greater cold, and ice coverage continued to expand during prolonged cooling intervals. As the frozen world took shape, ecosystems and landscapes continued to change in response. Cold-tolerant plants and animals spread into new areas, while those unable to endure the harsh conditions retreated or disappeared. Glaciers and ice sheets reshaped valleys, mountains, and coastal regions, leaving behind evidence of their slow movement. Ocean circulation, atmospheric patterns, and seasonal cycles adjusted to the cooler temperatures, creating a system in which cold conditions persisted over long periods. Through these processes, Earth transitioned gradually into a state dominated by ice. Polar regions remained covered year-round, glaciers advanced across continents, and seasonal cycles of freezing and melting extended farther into mid-latitudes. Sea levels fell as ice accumulated on land, exposing continental shelves and reshaping coastlines. Ocean currents slowed and shifted, distributing heat less effectively and reinforcing cooling trends. Atmospheric circulation carried cold air outward, and precipitation patterns supported the maintenance of ice sheets. Over millions of years, the planet's climate system adjusted to the new conditions. Life adapted to colder temperatures, with species evolving to survive in the presence of expanding ice. Landscapes were reshaped by glaciers, sediment deposition, and erosion. Ice-covered regions expanded gradually, covering areas that had once been warm or temperate. Oceans and rivers responded to the cooler environment, changing circulation, salinity, and habitat availability. In each of these processes, no single factor alone caused the shift, but the combination of solar fluctuations, atmospheric composition changes, ocean circulation patterns, ice growth, continental positions, volcanic activity, and orbital variations produced persistent cooling. Ice advanced in polar regions and moved toward lower latitudes. Glaciers carved valleys and shaped mountains. Oceans redistributed heat and altered salinity. Atmosphere circulation reinforced colder conditions. Ecosystems adjusted to the new climate. Evidence from geological records, including sediment cores, glacial deposits, and moraines, indicates the slow and continuous progression of cooling. These records capture cycles of ice growth and retreat, shifts in ocean temperature and chemistry, and the gradual adaptation of ecosystems to increasingly cold conditions. Life continued to exist, but the balance shifted toward species capable of surviving extended periods of cold, and landscapes reflected the ongoing dominance of ice. Over tens of millions of years, these processes accumulated. The repeated interaction of cold conditions, ice growth, changing ocean currents, shifting continents, volcanic influence, declining greenhouse gases, and variations in solar radiation maintained a trend in which frozen regions expanded steadily. Glaciers and ice sheets persisted and moved across continents. Sea ice covered larger areas of the oceans, and cold-adapted ecosystems spread. Through all of these changes, the world became increasingly dominated by ice. Rivers and lakes froze for longer periods, glaciers advanced, and ice sheets thickened. Ocean circulation and atmospheric patterns adjusted to colder conditions. Life responded to the environment, and landscapes were reshaped by the persistent influence of ice. Ice expanded gradually over continents and seas, reflecting the slow accumulation of many small changes that acted together over millions of years. As the planet continued to cool, the effects reached every part of the Earth. Polar regions were permanently frozen. Mid-latitudes experienced long winters and short, cool summers, and tropical regions experienced slightly lower temperatures and changes in precipitation. The planet's climate system stabilized around colder conditions, creating a frozen world in which ice was a constant presence. Sea levels remained lower as ice sheets persisted on land, exposing coastal areas that had previously been submerged. Continental shelves became land bridges, altering migration paths for species and the distribution of oceans. Ice sheets moved slowly, pressing down on land and reshaping the crust. Glaciers advanced, leaving behind moraines and valleys carved by ice. Mountains were modified as snow and ice accumulated and eroded surfaces. The accumulation of ice influenced ocean currents and atmospheric circulation. Cold, dense air from ice-covered regions flowed outward, affecting weather patterns and wind directions. Storm tracks shifted, precipitation changed, and regions far from the poles experienced colder conditions than before. Ocean currents redistributed heat less efficiently, reinforcing cold conditions and allowing ice to remain in regions where it might otherwise have melted. Over long periods, life adapted to this colder world. Species capable of surviving cold conditions spread into new regions. Species that could not tolerate freezing temperatures retreated or disappeared from areas covered by ice. Ecosystems reorganized to support life in a frozen environment, with plants and animals suited to cold climates dominating the landscape. The hydrological cycle adjusted to the presence of extensive ice. Evaporation decreased in colder regions, precipitation patterns changed, and rivers and lakes were influenced by prolonged periods of freezing. Freshwater systems froze for longer intervals, altering habitats and sedimentation patterns. These changes reinforced the dominance of cold-adapted ecosystems and contributed to the maintenance of ice across the globe. Through all these factors, Earth moved gradually into a frozen state. Ice sheets expanded, glaciers advanced, sea ice covered larger portions of the oceans, and cold-adapted species spread. Atmospheric and oceanic systems adjusted to the new climate. Landscapes were continuously reshaped by ice and the movement of glaciers. Rivers and lakes froze for longer periods, and sedimentation patterns changed. Life persisted in cold-adapted forms. The interactions of solar energy fluctuations, declining greenhouse gases, shifting continents, volcanic activity, ocean circulation changes, ice growth, and orbital variations continued to drive the gradual increase of ice coverage. Seasonal cycles became longer, summers warmer only enough to partially melt ice in some regions, and winters grew longer and colder. Ice sheets thickened, glaciers carved valleys, and landscapes reflected the persistent presence of ice. Geological records captured this slow progression. Sediment layers, glacial deposits, and moraines indicated the advance and retreat of ice over thousands and millions of years. These records showed that the transition to a frozen world occurred gradually, with periods of relative warmth followed by renewed cooling. Evidence of changing ocean chemistry, sediment deposition, and ecosystem adaptation demonstrates the persistent and cumulative effects of these gradual changes. Life continued to respond to these conditions. Species capable of surviving cold periods spread into regions newly covered by ice. Species that could not adapt were forced to retreat or disappeared from certain regions. Ecosystems evolved to cope with long winters, short summers, and extensive ice cover. Rivers and lakes froze for longer periods, altering freshwater habitats. Marine environments adjusted to changes in salinity, temperature, and ice coverage. Over millions of years, Earth's climate system stabilized around colder conditions. Ice sheets persisted on continents, glaciers advanced, and sea ice expanded over oceans. Ocean currents redistributed heat less efficiently, and atmospheric circulation carried cold air to lower latitudes. Life adapted to the persistent cold. Landscapes were continuously reshaped, and ice became a dominant feature across large parts of the planet. Every factor, from orbital variations to volcanic activity, greenhouse gas changes, ocean circulation shifts, and ice sheet growth, contributed to the gradual cooling. No single cause was solely responsible, but together they maintained the spread of ice and cold temperatures. Ice sheets advanced and thickened, glaciers reshaped valleys and mountains, and oceans and atmospheres adjusted to a colder environment. Through this long process, Earth became increasingly covered by ice. Polar regions remained frozen year-round. Mid-latitudes experienced long winters and cool summers. Tropical regions experienced slight cooling and changes in rainfall. Sea levels remained lower, exposing continental shelves. Glaciers pressed down on the crust, carved valleys, and deposited moraines. Ice influenced atmospheric and oceanic circulation. Life adapted to colder conditions, and ecosystems reorganized. Rivers and lakes froze for longer periods, sedimentation patterns changed, and landscapes reflected the persistence of ice. The movement of glaciers across the land has been a process that has shaped large parts of the Earth's surface over very long periods of time. Glaciers are enormous rivers of ice that slowly move under the influence of gravity. They form in places where the amount of snowfall over time is greater than the amount of snow that melts during warmer seasons. This accumulation of snow gradually compacts into ice, becoming dense and heavy enough to flow outward from its source. In the polar regions and in high mountains, glaciers can grow to incredible sizes, covering thousands of square kilometers. The weight of the ice causes the glacier to slowly push forward, pressing against rocks, soil, and vegetation in its path. When a glacier advances across a continent, it picks up fragments of rock and soil from the ground beneath it. These materials become embedded in the ice and are carried along as the glacier continues to move. The debris within the glacier, which can include everything from fine grains of silt to large boulders, is eventually deposited when the ice melts or breaks apart. These deposits, known as glacial till, can form large ridges called moraines, which mark the furthest points reached by the glacier. Moraines can stretch for many kilometers and provide a record of the glacier's movement over time. As the ice flows, it also carves and shapes the land beneath it. The pressure of the ice can erode the bedrock, smoothing some surfaces while creating deep grooves and striations in others. These marks in the rock are evidence of the glacier's passage and the immense force it exerts. Glaciers do not move at the same speed in all places. The center of a glacier often moves faster than the edges because the sides experience friction against the valley walls or the surrounding terrain. This uneven movement causes the ice to bend, crack, and form crevasses. Crevasses can be tens of meters deep and can stretch for hundreds of meters along the glacier's surface. They form because the ice is rigid enough to break under stress, yet flexible enough to slowly flow. As glaciers move, they also transport large amounts of water, which comes from melting ice at the glacier's base or surface. This meltwater can flow through channels within the ice or beneath the glacier, creating rivers that carve deep valleys and gorges. Over thousands of years, these meltwater channels can dramatically reshape the landscape. The extent of glaciers across continents has varied over millions of years. During the ice ages, vast ice sheets covered large portions of North America, Europe, and Asia. In North America, the Laurentide ice sheet spread across much of Canada and the northern United States. Its presence altered the drainage patterns of rivers, flattened hills, and carved deep lakes and basins. Some of the Great Lakes in the United States and Canada, for example, were formed as depressions in the land filled with water when the ice melted. In Europe, the Scandinavian ice sheet extended over much of Norway, Sweden, Finland, and parts of northern Germany and Poland. This ice sheet shaped fjords, valleys, and rolling hills, leaving behind moraines and drumlins that are still visible today. In Asia, glaciers in Siberia and the Himalayas influenced the course of rivers and created deposits that remain part of the landscape. Glaciers also move differently depending on the climate and the terrain. In areas with steep slopes, glaciers can move more quickly, forming narrow and elongated ice streams. In flatter areas, glaciers spread out and move more slowly, covering broader regions with ice. The thickness of the glacier also affects its movement. Thick ice exerts greater pressure on the ground beneath it, which can enhance basal sliding, where the ice slips over a layer of water or soft sediment at its base. Thinner glaciers may flow more slowly, and in some cases, they may become stagnant and cease to advance. The temperature of the ice is another factor. Glaciers in polar regions, where temperatures are extremely low, tend to have ice that is frozen to the bedrock and moves mostly by internal deformation. Glaciers in temperate regions, where temperatures are closer to the melting point, can slide more easily and produce more meltwater at their base. The formation of glacial landforms is a process that unfolds over thousands to millions of years. As glaciers move across the land, they shape valleys, creating U-shaped profiles that are distinct from the V-shaped valleys formed by rivers. They also create cirques, which are bowl-shaped depressions at the head of a glacier, and arêtes, which are sharp ridges between adjacent valleys. When glaciers retreat, meaning the ice melts faster than it advances, they leave behind a range of deposits. Terminal moraines mark the furthest point reached by the glacier, while recessional moraines indicate pauses in its retreat. Outwash plains form, where meltwater carries sediment away from the glacier, and drumlins, which are elongated hills of compacted till, provide clues about the direction of ice movement. Glacial movement is not constant over time. It can accelerate or slow down depending on changes in climate, snowfall, temperature, and the characteristics of the terrain. Periods of glacial advance, known as glacial maxima, occur when snowfall exceeds melting, allowing ice sheets and glaciers to grow. Periods of retreat, or interglacials, occur when melting exceeds snowfall, causing glaciers to shrink and expose previously covered land. These cycles have occurred repeatedly throughout Earth's history, particularly during the Pleistocene epoch, which began around 2,500,000 years ago and lasted until about 11,700 years ago. During this epoch, glaciers advanced and retreated multiple times, leaving a complex record of ice movement and deposition across continents. Glaciers also have a significant impact on ecosystems. As they advance, they can remove vegetation and alter habitats, forcing plants and animals to move to new areas. As they retreat, they create new landforms and expose fresh soil, allowing vegetation to recolonize. This dynamic process shapes the distribution of species and the development of ecosystems over long timescales. In polar regions, glaciers interact with sea ice and the ocean, influencing local climate and ocean currents. The melting of glaciers contributes fresh water to the oceans, which can affect salinity and circulation patterns. Glacial ice itself records information about past climates. Snow that falls on a glacier each year becomes compacted into layers of ice, preserving tiny air bubbles that contain samples of the atmosphere from the time the snow fell. Scientists can study these ice cores to learn about temperature, precipitation, and atmospheric composition over hundreds of thousands of years. By analyzing isotopes, trapped gases, and particulate matter, researchers can reconstruct past climate conditions and gain insights into how glaciers responded to changes in temperature and precipitation. These studies show that glaciers are sensitive indicators of climate, reflecting long-term shifts as well as short-term variations. The speed at which glaciers move can vary widely. Some glaciers flow only a few centimeters per year, while others can move tens of meters annually. Ice streams within large ice sheets can flow even faster, carrying ice from the interior of the sheet to the ocean. The flow of glaciers is influenced by internal deformation of the ice, basal sliding over the bed, and the presence of meltwater. In addition, glaciers can surge, a sudden increase in flow rate that can last for a few years or decades. Surges are caused by changes in basal conditions, the buildup of stress within the ice, or variations in meltwater distribution. Glaciers leave behind a variety of landforms that provide clues about their history. Striations are scratches on bedrock caused by rocks embedded in the ice scraping along the surface. Roches moutonnées are asymmetric hills of bedrock shaped by glacial erosion. Kettles are depressions formed when blocks of ice become buried in sediment and melt, leaving behind a hole that can fill with water. Eskers are long, winding ridges of sand and gravel deposited by meltwater streams flowing within or beneath a glacier. These features can be found across formerly glaciated regions, providing evidence of the glacier's extent and movement patterns. Glacial deposits are important for understanding Earth's history. Till, which consists of unsorted sediment carried by the ice, can reveal the direction and speed of glacier flow. Outwash, composed of sediment deposited by meltwater, shows the influence of water on glacial landscapes. These deposits can include clay, silt, sand, gravel, and boulders, reflecting the range of materials transported by the ice. Over time, glacial deposits contribute to soil development, influence drainage patterns, and create natural resources such as sand, gravel, and clay for human use. Glaciers also affect sea levels. When large ice sheets grow, they store vast amounts of water on land, lowering global sea levels. When glaciers melt and retreat, this water returns to the oceans, raising sea levels. These changes can have far-reaching effects on coastal regions, river deltas, and low-lying areas. Throughout Earth's history, fluctuations in glacial volume have led to periods of rising and falling sea levels, which are recorded in sedimentary deposits along coastlines and in ocean basins. The study of glaciers, known as glaciology, involves observation, measurement, and modeling of ice movement and its effects on the landscape. Scientists measure glacier thickness, flow speed, surface elevation, and meltwater production to understand how glaciers behave. Remote sensing technologies, including satellites and aerial photography, allow researchers to monitor glaciers over large areas and track changes over time. Field studies involve drilling ice cores, measuring snow accumulation, mapping moraines, and analyzing sediment deposits. These methods provide data that help scientists understand past glacial events, current glacier dynamics, and potential future changes. Glaciers respond to both natural and human influences. Natural variations in climate, such as changes in temperature, precipitation, and volcanic activity, affect glacier growth and retreat. Human activities, including the emission of greenhouse gases, can influence global temperatures and contribute to glacier melting. Observations over the past century show that many glaciers worldwide have been retreating at unprecedented rates. Monitoring these changes provides valuable information about the interactions between glaciers, climate, and ecosystems. The ice within glaciers is not uniform. It consists of layers formed over many years with varying density, crystal structure, and air content. The upper layers of a glacier, called the firn, consist of compacted snow that has survived at least one summer melt season. Below the firn, the ice becomes denser as air bubbles are compressed and the crystal structure rearranges. The bottom layers, in contact with the bedrock, are subject to friction, pressure, and melting. The internal structure of a glacier affects its flow behavior, the formation of crevasses, and the movement of meltwater. Glacial movement can create hazards. Rapid advances or surges can block rivers, creating temporary lakes that may burst and cause flooding. Ice avalanches and falling seracs, which are large blocks of ice, can pose dangers to people and animals in glaciated regions. Glacier retreat can destabilize slopes, leading to landslides. Despite these risks, glaciers are also valuable sources of fresh water. Meltwater from glaciers feeds rivers, supports agriculture, and sustains ecosystems, particularly in regions where seasonal rainfall is limited. Glaciers have existed on Earth for millions of years. The earliest evidence of glaciation dates back to the Precambrian, more than 600 million years ago, when ice sheets covered parts of the continents. During the Phanerozoic Eon, glaciers advanced and retreated multiple times, shaping landscapes and influencing sea levels. The most recent major glaciation, the last glacial maximum, occurred approximately 21,000 years ago when ice sheets reached their greatest extent. Since then, glaciers have been retreating, leaving behind valleys, lakes, and moraines that provide a record of their former presence. The interaction between glaciers and rock is a continuous process. Glacial erosion occurs through plucking, where the ice lifts blocks of rock from the ground, and abrasion, where debris in the ice grinds against the bedrock. This erosion can remove vast amounts of material over time, altering the shape of mountains, valleys, and plains. The patterns of erosion are recorded in the landscape, providing information about the direction, speed, and thickness of past glaciers. Glaciers also transport sediment over long distances. Rocks and soil picked up at the glacier's origin can be carried for hundreds of kilometers before being deposited. This process distributes minerals and nutrients across large areas, influencing soil composition and the potential for plant growth. Glacial deposits are often layered, reflecting changes in ice flow, melting rates, and sediment supply. Studying these layers allows scientists to reconstruct the history of glaciation and understand the forces that shape the continents. The size and shape of glaciers can vary widely. Valley glaciers occupy narrow mountain valleys and are typically long and thin. Ice caps cover larger areas but are less than 50,000 square kilometers in size, while ice sheets are much larger, exceeding 50,000 square kilometers. The Antarctic and Greenland ice sheets are the largest on Earth, containing the majority of the planet's fresh water. Their movement influences global climate, sea levels, and ocean currents. Smaller glaciers in mountain ranges around the world respond more quickly to changes in temperature and precipitation, making them sensitive indicators of regional climate conditions. Glaciers influence human history and settlement. Many rivers that originate from glaciers have been essential for irrigation, drinking water, and transportation. Glacial valleys provide routes for roads, railways, and human migration. The sediments left by glaciers, including fertile soils and sand and gravel deposits, have been important for agriculture, construction, and industry. The study of glacial geology has also contributed to understanding natural hazards, resource distribution, and landscape evolution. Glaciers have a seasonal cycle. In colder months, snowfall adds to the glacier's mass, while in warmer months, melting reduces it. The balance between accumulation and ablation, or ice loss, determines whether a glacier advances or retreats. This cycle varies depending on latitude, altitude, and local climate conditions. In high mountain regions, glaciers may persist for centuries or millennia, even with seasonal melting, because the accumulation of snow outweighs losses from melting and sublimation. The presence of glaciers affects local climate. Large ice sheets reflect sunlight, influencing temperatures in nearby regions. The cooling effect of glaciers can affect atmospheric circulation and precipitation patterns. In addition, glaciers release fresh water into rivers and oceans, which can impact the salinity, temperature, and movement of ocean currents. These processes play a role in shaping regional and global climate patterns over long periods of time. The retreat of glaciers exposes land that has been covered for thousands of years. Newly exposed surfaces can undergo rapid changes, with vegetation colonizing bare ground and soils developing over time. Glacial lakes may form in depressions left by melting ice, creating habitats for aquatic species. The newly available land also allows for human use, including agriculture, settlements, and resource extraction. Over time, these areas continue to evolve, influenced by climate, hydrology, and ecological processes. The study of past glaciers helps scientists understand Earth's climate history. Glacial deposits, landforms, and ice cores provide evidence of temperature fluctuations, precipitation patterns, and atmospheric composition over millions of years. By examining these records, researchers can identify periods of glacial advance and retreat, the timing of ice ages, and the responses of glaciers to environmental changes. This knowledge contributes to understanding long-term climate trends and the interactions between ice, land, water, and atmosphere. Glaciers are constantly changing. Even within a single year, the surface of a glacier can be transformed by snowfall, melting, calving, and the movement of ice. Over centuries, glaciers can advance across entire valleys and cover large regions, then retreat to leave behind moraines, drumlins, and outwash plains. The processes of erosion, deposition, and ice flow are continuous, shaping the land and providing a record of environmental conditions. The dynamics of glaciers are influenced by both external and internal factors. External factors include climate, snowfall, temperature, and the characteristics of the bedrock or sediment beneath the ice. Internal factors involve the properties of the ice itself, including its temperature, crystal structure, and the presence of meltwater. The interplay between these factors determines the speed, direction, and extent of glacier movement. Glaciers have existed in various forms and sizes throughout Earth's history. During periods of extensive glaciation, ice sheets covered much of the northern hemisphere, while smaller glaciers persisted in high mountains and polar regions. During warmer periods, glaciers retreated, leaving behind deposits and landforms that record their presence. This cycle of growth and shrinkage has repeated many times, producing a complex and varied landscape shaped by ice. Glacial landscapes provide evidence of the past presence of ice. Features such as U-shaped valleys, cirques, arêtes, moraines, drumlins, eskers, kettles, and striated bedrock indicate the direction, extent, and behavior of glaciers. By studying these features, scientists can reconstruct the history of ice movement, the processes of erosion and deposition, and the interactions between glaciers and the environment. The movement of glaciers continues to affect regions where they exist today. In polar areas, glaciers advance and retreat slowly, shaping the terrain, influencing ecosystems, and contributing freshwater to rivers and oceans. In mountain regions, glaciers respond more quickly to seasonal and long-term climate changes, creating dynamic landscapes. The study of contemporary glaciers provides insights into the processes that have operated throughout Earth's history, the responses of ice to environmental changes, and the ongoing interactions between glaciers, land, and water. Glaciers also play a role in shaping rivers and lakes. As they advance, they can block existing river channels, creating lakes or redirecting flow. When they retreat, meltwater can carve new channels and form lakes in depressions left by the ice. The sediment carried by glaciers is deposited in valleys, plains, and river deltas, influencing the topography and fertility of these regions. These processes continue to shape landscapes, influence ecosystems, and provide resources for human use. The processes of glacial advance and retreat, erosion, deposition, and ice flow are continuous and interconnected. Glaciers move under their own weight, erode bedrock, transport sediment, deposit material, and reshape the land over thousands to millions of years. These processes create a record of past environmental conditions, influence present landscapes, and provide resources and habitats for living organisms. Glaciers are dynamic components of the Earth's system, reflecting the interactions between climate, ice, water, and land. Over time, the patterns of glacial movement, accumulation, and melting leave a detailed record in the land. Moraines, drumlins, eskers, kettles, striations, and other features reveal the direction, speed, and extent of glaciers. Ice cores preserve information about past climates, including temperature, precipitation, and atmospheric composition. Sediment deposits record the material transported by glaciers, the processes of erosion and deposition, and the changes in land and water systems. These records provide a window into the long history of glaciers on Earth and their influence on the environment. The processes of glaciation have occurred repeatedly throughout Earth's history. Ice sheets have grown and retreated many times, covering continents and shaping landscapes. Glaciers have advanced and retreated in response to climatic fluctuations, influencing sea levels, river systems, soil development, and ecosystems. The landforms and deposits left by glaciers provide a record of these events, allowing scientists to reconstruct the timing, extent, and impact of glaciation over millions of years. Beneath the thick layers of ice that cover vast parts of the Earth, there exists a hidden environment of valleys, mountains, rivers, and lakes. These structures are carved and shaped over millions of years through the slow but persistent movement of ice and the action of water that flows under it. In areas such as Greenland and Antarctica, the ice can be several kilometers thick, pressing down on the land with immense weight. Under this ice, temperatures remain extremely low, but the pressure and friction from the moving ice create conditions where liquid water can exist, allowing rivers to flow and lakes to form, even though the surface remains frozen. The discovery of these hidden valleys began with early attempts to measure ice thickness and map the shape of the land beneath. Scientists use techniques such as radar, which can penetrate ice to detect what lies underneath, revealing long valleys, sharp ridges, and deep basins. These valleys can be hundreds of kilometers long and several kilometers deep, creating a network of terrain that was previously unknown to human knowledge. Some of these valleys are larger than those found above ground in familiar landscapes, but they are entirely buried beneath ice that may be hundreds of meters thick. The hidden landscapes beneath ice sheets have been studied carefully because they hold important clues about Earth's history. The valleys and basins show evidence of past glacial movements and can reveal how the climate has changed over tens of thousands or even millions of years. For example, scientists can analyze the shape of these valleys and the sediments found within them to understand how ice advanced and retreated during different ice ages. The presence of deep lakes beneath ice is particularly interesting because these lakes remain isolated from the surface, often for millions of years, preserving ancient water that can provide information about life in extreme conditions. Some of these lakes, such as Lake Vostok in Antarctica, have been sealed under ice for more than 15 million years, and the water within them contains unique microorganisms that have adapted to survive without sunlight and in near-freezing temperatures. These microorganisms offer valuable insights into how life can exist in harsh environments, and they may even serve as models for understanding the possibility of life on other planets or icy moons in our solar system. The formation of valleys beneath ice occurs through a combination of ice movement, melting, and the action of water. As glaciers and ice sheets slowly move across the land, they exert immense pressure on the underlying rock and sediment. This pressure can cause the ice to melt slightly at the base, creating a thin layer of water that allows the ice to slide. Over time, this sliding action erodes the rock and soil below, carving out valleys and channels that can stretch for hundreds of kilometers. In some regions, the ice also acts as a conveyor, carrying rocks and sediment along its base, which further sculpts the hidden landscape. These processes are extremely slow, occurring over thousands or millions of years, but the result is a complex and intricate network of landforms beneath the ice. Exploration of these hidden valleys has been aided by technological advancements. Radar systems, both airborne and ground-based, allow scientists to map the thickness of ice and the topography beneath it. Satellites equipped with radar and other sensing instruments can measure subtle changes in ice surface elevation, indicating the presence of underlying valleys or lakes. In addition to radar, seismology has been used to study the land beneath ice by observing how seismic waves travel through ice and rock. By combining data from multiple methods, scientists can create detailed maps of the subglacial environment, revealing features such as mountains, valleys, ridges, and lakes with remarkable clarity. The valleys beneath ice sheets are not uniform. They exhibit a wide variety of shapes and sizes. Some are narrow and steep-sided, resembling canyons, while others are broad and shallow. These differences depend on factors such as the type of rock beneath the ice, the direction and speed of ice movement, and the presence of water at the base. In certain regions, entire networks of valleys intersect, forming complex drainage systems that channel water beneath the ice. These subglacial rivers and streams can transport sediments, reshape the valleys, and even influence the movement of the ice above. Understanding these water systems is crucial because they play a key role in controlling ice flow and stability, which has implications for sea level and climate studies. Beneath the ice, valleys often contain hidden lakes, some of which are very large. Lake Vostok, one of the largest subglacial lakes, is more than 250 kilometers long and 50 kilometers wide. Its depth reaches approximately 800 meters in certain places. This lake is covered by more than 4 kilometers of ice, isolating it from the atmosphere for millions of years. Other subglacial lakes are smaller but still significant, such as Lake Whillans, which is about 25 kilometers long and flows beneath the West Antarctic ice sheet. These lakes remain liquid due to the combination of pressure from the overlying ice and geothermal heat rising from the Earth's interior. The ecosystems within subglacial lakes are remarkable. Microorganisms living in these lakes have adapted to survive in complete darkness, low temperatures, and limited nutrients. They derive energy from chemical reactions involving minerals and dissolved gases rather than sunlight. Scientists study these microorganisms not only to understand life in extreme conditions, but also to learn how such ecosystems respond to changes over time. By examining DNA and metabolic processes, researchers can uncover evolutionary strategies that have allowed these life forms to persist in isolation for millions of years. These studies provide insight into the resilience of life and expand our understanding of the diversity of ecosystems on Earth. The valleys beneath ice sheets also reveal information about past glacial dynamics. When ice sheets grow, they push rocks and sediment outward, and when they retreat, they leave behind evidence of erosion and deposition. Sediment layers collected from subglacial valleys show alternating periods of ice advance and retreat, which correspond to historical climate fluctuations. Some valleys contain deep deposits of till, which is unsorted sediment left by glaciers, while others have well-stratified layers formed by water flow beneath the ice. By studying these layers, scientists can reconstruct the history of ice sheet movement, providing a record of Earth's climate over hundreds of thousands of years. Hydrology beneath ice is complex. Water exists in various forms, from thin films at the base of glaciers to flowing rivers and large lakes. Subglacial rivers can flow at speeds of several meters per second, and their paths are influenced by the shape of the valleys and the pressure of the overlying ice. These rivers can transport sediments and nutrients, shaping the landscape and influencing ice dynamics. In some areas, water accumulates in depressions to form subglacial lakes, which can remain stable for millions of years or occasionally drain rapidly, affecting ice movement above. Monitoring these water systems is essential for understanding how ice sheets respond to environmental changes. The valleys and landscapes beneath ice are not static. They change over time as ice moves, melts, and refreezes. Subglacial erosion can deepen valleys, while sediment deposition can fill depressions and alter the flow of water. Seasonal and long-term variations in ice flow can also create temporary lakes and streams, which may appear and disappear over time. These dynamic processes mean that the hidden landscapes beneath ice are continuously evolving, shaped by both the physical properties of ice and the presence of water. In addition to the scientific interest, these hidden landscapes have practical implications. Understanding subglacial topography is important for predicting how ice sheets will respond to climate change and how they might contribute to sea level rise. Valleys and lakes beneath ice influence the speed at which ice flows toward the ocean, and changes in these subglacial features can accelerate or slow ice movement. Accurate maps of subglacial landscapes are therefore essential for climate models and for planning scientific research in polar regions. Subglacial valleys also have potential for revealing ancient geological features. The rock beneath ice sheets may contain fossils, mineral deposits, and other evidence of past environments. By accessing these areas, scientists can study conditions that existed long before the ice formed. Some valleys contain ancient river channels and glacial deposits that date back millions of years, providing a window into Earth's distant past. These discoveries can help to reconstruct the evolution of continents, the history of climate, and the processes that shape the planet's surface over geological time. The methods used to explore subglacial landscapes continue to advance. In addition to radar and seismology, ice-penetrating sonar and drilling techniques have been developed. These methods allow researchers to obtain direct samples of ice, water, and sediments from beneath the ice sheets. Drilling into subglacial lakes requires careful techniques to avoid contamination, and specialized instruments are used to measure temperature, chemical composition, and microbial life. Data collected from these explorations provide detailed information about the physical and biological characteristics of hidden valleys and lakes, enhancing our understanding of this remote environment. The hidden valleys beneath ice also show evidence of tectonic activity. In some regions, the bedrock beneath ice sheets is affected by faulting, folding, and other geological processes. These features influence the shape and direction of valleys, and they can also affect the flow of ice. In areas where tectonic forces are strong, subglacial valleys may align with faults or follow zones of weaker rock, guiding the movement of water and ice. Understanding the interaction between tectonics and subglacial landscapes is important for interpreting the geological history of polar regions. Subglacial landscapes are home to unique chemical environments. The water in subglacial lakes often contains dissolved gases such as carbon dioxide, methane, and oxygen, as well as minerals leached from the surrounding rock. These chemical components interact with microorganisms, providing energy sources and influencing biological activity. Researchers study the chemistry of subglacial waters to understand how life can be sustained in extreme conditions and to identify potential analogs for extraterrestrial environments. The chemical composition of subglacial lakes also affects ice melting and refreezing processes, contributing to the dynamics of the ice sheet. The study of hidden landscapes beneath ice continues to reveal surprising discoveries. Scientists have identified channels that extend for hundreds of kilometers, connecting multiple lakes and forming extensive subglacial drainage networks. Some valleys contain large accumulations of sediment that may represent ancient river deposits, while others have features shaped primarily by ice movement. These discoveries show that the hidden environment beneath ice is far more complex than previously imagined, with diverse terrain, active water systems, and unique ecosystems. Exploration of subglacial valleys is also important for understanding natural hazards. Sudden drainage of subglacial lakes can lead to outburst floods that affect ice flow and can reach the ocean. Monitoring the stability of these lakes and the surrounding valleys helps scientists assess potential risks associated with rapid changes in ice sheet dynamics. This knowledge is valuable for predicting the impact of environmental change on polar regions and for preparing for possible effects on sea level and coastal areas. The valleys beneath ice are connected to the broader climate system. Changes in temperature, precipitation, and ice sheet mass affect the flow of ice and the movement of water beneath it. Conversely, the dynamics of subglacial valleys influence the rate at which ice sheets lose mass to the ocean. Understanding these connections is crucial for interpreting observations of polar regions and for predicting future changes. Subglacial landscapes are therefore an integral part of Earth's climate system, interacting with ice, water, and the atmosphere over both short and long time scales. The hidden valleys under ice are home to geological features that can reveal past environmental conditions. Layers of sediment and rock within the valleys contain information about glacial cycles, volcanic activity, and the presence of ancient ecosystems. By analyzing these layers, scientists can reconstruct the timing and extent of past glaciations, the types of environments that existed before the ice, and the processes that shaped the continents. This information contributes to our understanding of Earth's long-term history and the forces that have shaped the planet's surface over millions of years. Research into subglacial valleys has also contributed to understanding ice sheet behavior. The topography beneath ice sheets affects how ice flows and responds to stress. Valleys can act as channels guiding ice movement, while ridges and high points can slow ice flow or create areas of compression. Mapping these features allows scientists to model ice dynamics more accurately and to predict how ice sheets might evolve under different climate scenarios. This research is essential for understanding the stability of ice sheets and their potential impact on global sea levels. The discovery of new subglacial lakes and valleys continues at a rapid pace. Each new finding adds to the complexity of our understanding, revealing that beneath the ice there are interconnected systems of water, sediment, and rock. Some valleys are filled with thick layers of sediment that preserve a record of past ice sheet behavior, while others contain deep water channels that influence ice flow. These discoveries highlight the diversity and dynamism of the subglacial environment, showing that even beneath kilometers of ice, Earth remains active and evolving. The ecosystems of subglacial lakes provide insights into evolutionary processes. Microorganisms in these lakes have developed unique adaptations to survive in conditions that include complete darkness, high pressure, low temperatures, and limited nutrients. They utilize chemical reactions for energy and have metabolic pathways different from surface organisms. Studying these life forms helps scientists understand how organisms adapt to extreme conditions, the limits of life on Earth, and the potential for life in similar environments beyond our planet. Subglacial valleys also play a role in ice sheet hydrology and stability. Water stored in lakes and flowing through rivers beneath the ice can lubricate the base of glaciers, affecting their speed and direction. Changes in subglacial water volume can lead to variations in ice flow, which may result in acceleration or slowing of ice toward the ocean. These processes are essential for understanding how ice sheets interact with climate and how changes in the subglacial environment can influence global sea levels. The chemical and biological characteristics of subglacial lakes are diverse. Some lakes have high concentrations of dissolved oxygen, while others have low oxygen levels. Certain lakes contain methane or other gases that can influence chemical reactions and microbial activity. These variations are influenced by the history of ice coverage, the input of minerals from bedrock, and the isolation of the lake from the atmosphere. By studying these chemical environments, Scientists can learn about the processes that sustain life in extreme conditions and the factors that control subglacial ecosystems. Hidden valleys beneath ice are also linked to the study of planetary analogs. The conditions found in subglacial lakes and valleys on Earth are similar to those that may exist on icy moons such as Europa or Enceladus. The presence of liquid water, pressure, ice cover, and chemical gradients provides a natural laboratory for studying how life could exist elsewhere in the solar system. Research in these environments informs the planning of future space missions and helps identify potential habitats for extraterrestrial life. The valleys under ice continue to be mapped and studied using advanced technologies. Airborne radar, satellite measurements, ground surveys, and deep drilling programs provide complementary information about topography, ice thickness, water presence, and sediment layers. Integration of these data sets produces detailed three-dimensional models of subglacial landscapes, revealing their complexity and variation. These models help scientists understand the processes shaping valleys, lakes, and water systems beneath ice sheets and improve predictions of future changes in polar regions. The sediment layers in subglacial valleys hold important information about glacial history. These layers can include clay, silt, sand, and gravel, each providing clues about the flow of water and ice in the past. Analysis of these sediments can reveal the timing of ice sheet advances and retreats, the intensity of glacial erosion, and the presence of ancient lakes or rivers. In some cases, sediments may contain fossilized microorganisms or chemical signatures that offer insight into past biological activity. These findings contribute to understanding the long-term evolution of subglacial landscapes and the interactions between ice, water, and life. Valleys beneath ice can interact with each other to form complex drainage systems. Subglacial rivers often follow paths determined by the topography of the valleys, connecting multiple lakes and channels. These networks can span hundreds of kilometers, allowing water and sediments to be transported across large areas beneath ice sheets. Seasonal and long-term changes in water flow can modify the drainage system, creating new channels, redirecting rivers, or forming temporary lakes. Understanding these interactions is essential for modeling ice sheet behavior and predicting responses to environmental changes. The discovery of unique microorganisms in subglacial lakes has implications for understanding the limits of life on Earth. These organisms survive in extreme cold, under high pressure, and without sunlight, relying on chemical energy rather than photosynthesis. Studying their metabolism, genetic adaptations, and interactions with the chemical environment provides insights into evolutionary strategies that allow life to persist under challenging conditions. These findings expand our knowledge of biodiversity and inform the search for life in extreme environments on Earth and beyond. Exploration of subglacial valleys involves collaboration between multiple scientific disciplines. Geologists, glaciologists, biologists, chemists, and engineers work together to map the terrain, analyze sediments, study microorganisms, and understand water chemistry. This multidisciplinary approach is necessary because the subglacial environment is complex, involving interactions between physical, chemical, and biological systems. By combining expertise, researchers can gain a more complete understanding of hidden valleys, lakes, and ecosystems beneath the ice. The movement of ice over valleys also produces distinctive landforms. As glaciers advance and retreat, they can leave behind ridges, moraines, and other features that reflect the direction and speed of ice flow. These landforms provide information about the dynamics of ice sheets and the history of glaciation in a region. In some cases, the valleys themselves influence the shape of the overlying ice, guiding its movement and creating patterns that can be observed from satellites. Subglacial valleys are shaped not only by ice but also by the interaction with underlying rock. The type of rock, its hardness, and the presence of faults or fractures influence how easily the ice can erode and reshape the landscape. Softer rocks may be more quickly carved into deep valleys, while harder rocks resist erosion and create ridges or high points. These geological characteristics help determine the overall topography of subglacial landscapes and influence the flow of ice and water above. The valleys beneath ice sheets are dynamic, ever-changing environments. They evolve through a combination of ice movement, melting, sediment deposition, water flow, and chemical interactions. These processes operate on timescales ranging from days to millions of years, creating a constantly shifting landscape beneath the ice. By studying these processes, scientists gain insight into how Earth's polar regions function and how they have changed over time. The study of hidden landscapes and valleys beneath ice is ongoing and continues to reveal new features. Each new discovery adds to the understanding of ice sheet dynamics, subglacial ecosystems, geological history, and the potential for life in extreme environments. Through the use of advanced technologies, careful sampling, and interdisciplinary research, the complex and fascinating world beneath the ice is gradually being revealed. The interplay of ice, water, rock, and life beneath the ice sheets demonstrates the complexity of these hidden landscapes. Valleys guide water flow, influence ice movement, and create habitats for microorganisms. Sediment layers preserve a record of past glacial events, while chemical environments provide energy sources for life. Tectonic features shape the valleys, and subglacial lakes act as reservoirs that can affect ice stability. Together, these elements form a system that is interconnected, dynamic, and continually evolving, offering a window into a part of Earth that is largely hidden from view. The Earth's surface has been shaped over thousands of years by cycles of freezing and thawing that occur repeatedly in different regions. This rhythm of freezing and thawing has a deep influence on landscapes, soils, water systems, and even the movement of materials over large distances. When temperatures drop below the freezing point of water, liquids in the ground and in surface environments begin to solidify. This solidification changes the physical properties of the materials present, including soil, rock, and water. Ice is less dense than liquid water, which causes expansion as water freezes. This expansion exerts pressure on surrounding materials, creating cracks, fractures, and movement in rocks and soil. When temperatures rise again above the freezing point, ice melts back into liquid water, which can flow through previously frozen materials, carrying fine particles and larger debris along with it. Over thousands of years, these repeated cycles of freezing and thawing slowly alter the landscape, creating valleys, depressions, hills, and ridges in areas affected by seasonal and long-term temperature changes. In regions where this rhythm occurs most frequently, such as near the poles or at high elevations, soils and surfaces are subjected to continuous stress from the formation and melting of ice. Permafrost, which is ground that remains frozen for 2 or more consecutive years, is an important feature in these areas. It preserves a record of past climate conditions and controls the distribution of water within the soil. The active layer, which is the top portion of permafrost that thaws in the warmer months, undergoes seasonal cycles of freezing and thawing. These cycles cause movement in the soil known as frost heaving, which lifts soil and stones and rearranges particles over time. The repeated rise and fall of the active layer reshapes the terrain in a gradual manner, moving small rocks and sediments down slopes and forming hummocks, terraces, and polygonal patterns that can extend for kilometers. In some cases, entire hillsides slowly creep downward as the ice within the soil melts and water flows, transporting material to lower regions. Water plays a central role in the rhythm of freezing and thawing. When ice melts, it creates meltwater that infiltrates into the ground, sometimes refreezing later during colder periods. This water can expand existing cracks and loosen sediments, which contributes to erosion and sediment transport. Meltwater flowing over the surface can carve channels and small streams in landscapes that are otherwise frozen for much of the year. Over thousands of years, repeated meltwater flows deepen channels and shape valleys in regions where glaciers and seasonal ice are present. Sediments carried by water are deposited in lower areas, forming alluvial fans, deltas, and small basins. The size of these features grows gradually, depending on the frequency and intensity of freeze-thaw cycles. Ice in rivers and lakes can also contribute to landscape changes. When surface water freezes, it can lift sediments and rocks as ice expands. During thawing periods, ice fragments may move downstream, carrying material along with them and reshaping riverbeds and shorelines over time. The influence of the freezing and thawing rhythm is not limited to the surface. Underground systems, such as caves, tunnels, and bedrock fractures, are affected as water penetrates cracks and refreezes. Ice within fractures expands and causes the rock to break into smaller pieces. Over thousands of years, this slow process contributes to the widening of cracks and the formation of underground cavities. In regions with sedimentary rocks, repeated freezing and thawing can fragment layers, allowing water to penetrate deeper and transport fine particles to other areas. This process gradually alters the composition and texture of soils, making some areas more porous and others more compact. Soil profiles, which record the arrangement of different layers of sediments, are influenced by the repeated rise and fall of temperature. Organic matter within soil may also be preserved in frozen layers and released slowly when thawed, providing nutrients to plants and microorganisms when conditions allow. Glaciers, which are massive bodies of ice, are a direct result of prolonged periods of freezing. They grow as snowfall accumulates and compresses into ice, often over thousands of years. As glaciers expand, they follow the underlying slope of the land, moving slowly under their own weight. The movement of glaciers, combined with freezing and thawing at their edges, shapes the terrain. Rocks and debris trapped in ice are transported along the glacier's path, scraping and grinding surfaces as they move. When the glacier melts or retreats during warmer periods, sediments and rocks are deposited in new locations, forming moraines, drumlins, and other glacial landforms. These features record the advance and retreat of ice over millennia, reflecting periods of colder and warmer climate. Glacial meltwater also contributes to rivers and lakes, which continue to shape valleys and basins after the ice has disappeared. The cycles of freezing and thawing within and around glaciers affect both the ice itself and the landscapes in contact with it. Temperature fluctuations over thousands of years influence the size and thickness of ice layers in permafrost, glaciers, and seasonal snow cover. During colder periods, ice thickens as more water freezes and accumulates, while warmer periods cause melting and redistribution of materials. The rate of freezing and thawing can vary depending on factors such as latitude, altitude, sunlight exposure, wind, and precipitation. These factors interact to produce local variations in how materials are moved, how water infiltrates, and how soils and rocks respond. Even in areas far from glaciers, seasonal freeze-thaw cycles can cause significant changes. Soil frost can lift pavements, create cracks in roads, and move boulders, demonstrating the power of repeated cycles over time. In natural landscapes, small-scale changes gradually accumulate into larger transformations that alter the overall appearance and structure of the terrain. Vegetation and living organisms are affected by the rhythm of freezing and thawing. In regions where the active layer of permafrost thaws during warmer months, plants can grow and take advantage of moisture and nutrients released by melting ice. Roots penetrate the soil, breaking up frozen layers and allowing water to circulate. Microorganisms and small invertebrates benefit from thawed soils, which support decomposition and nutrient cycling. When temperatures drop and the soil refreezes, water becomes locked in ice, temporarily limiting biological activity. Over thousands of years, the alternating periods of freezing and thawing influence which species can survive, where they can grow, and how ecosystems develop. Vegetation also affects soil stability, as roots can hold particles in place during thawing periods, slowing erosion and the movement of sediments. The rhythm of freezing and thawing is evident in large-scale geological records. Sediment layers in lakes, riverbeds, and coastal regions often contain evidence of past freeze-thaw activity. Ice wedges, formed when water repeatedly freezes in cracks and expands, create distinctive polygonal patterns in sediments. Loess deposits, which are fine particles carried by wind and sometimes reworked by meltwater, reflect cycles of cold and warm periods. Fossils preserved in frozen ground or sediment layers provide information about plants and animals that lived in areas affected by freezing and thawing. These records allow scientists to reconstruct past climates, showing periods when ice expanded or retreated and how landscapes responded to these changes. The distribution of sediments, rocks, and ice features over wide areas provides a visible map of the history of freezing and thawing cycles. Rivers and lakes in cold regions are closely connected to freeze-thaw processes. Ice formation on rivers and lakes can lift sediments, redirect flow, and create temporary dams. When ice melts, water levels rise and carry particles downstream. Flooding events caused by rapid thawing can deposit large amounts of sediments over floodplains, forming layers that record repeated cycles of freezing and thawing. Seasonal ice cover affects temperature and oxygen levels in water, influencing aquatic life and the decomposition of organic matter. In permafrost regions, thermokarst lakes form when ice-rich ground melts, causing the surface to collapse and fill with water. These lakes grow, shrink, and sometimes drain entirely depending on the ongoing rhythm of freezing and thawing. Wind and precipitation interact with freeze-thaw cycles to move sediments over time. Snow accumulation adds weight to ice layers and increases pressure in frozen soils, while melting snow releases water that can erode slopes and transport materials. Wind can blow fine particles over frozen surfaces, which later settle when ice melts. This redistribution of sediments occurs gradually, but has a long-term impact on the shape and composition of landscapes. Dust and sand carried by wind may accumulate in depressions, later compacted by ice formation, forming distinct layers that can be recognized in geological records. Over thousands of years, these processes contribute to the complexity and diversity of landforms in cold regions. Human activity can also interact with the rhythm of freezing and thawing. In areas where soil freezes and thaws annually, structures built on the ground experience stress, and roads, buildings, and pipelines may be affected by frost heaving and soil movement. Traditional practices in some regions have adapted to these cycles by timing construction, agriculture, and transportation to correspond with frozen or thawed conditions. In modern times, engineering approaches account for freeze-thaw cycles to prevent damage to infrastructure. Observing and understanding the long-term effects of freezing and thawing on landscapes helps humans plan settlements, agriculture, and transportation networks in regions affected by these cycles. The rhythm of freezing and thawing extends beyond Earth's surface to ice sheets and polar environments. The Greenland ice sheet and the Antarctic ice sheet experience variations in temperature that influence the thickness and movement of ice over thousands of years. Seasonal melting on the surface creates meltwater streams that flow into crevasses and basal layers, lubricating ice movement and transporting sediments. Ice cores drilled from these ice sheets contain records of past temperature changes, snowfall, and atmospheric conditions. The trapped gases and particles within ice cores provide detailed information about the environment at the time the ice formed. Analysis of these cores reveals patterns of freezing and thawing that occurred over tens of thousands of years, showing the slow changes in climate and ice distribution over vast areas. The structure of permafrost is strongly influenced by repeated cycles of freezing and thawing. Ice lenses, formed by the accumulation of water that freezes in layers, expand over time and create patterned ground. When thawing occurs, the ground subsides in some areas and water collects in depressions. These changes affect drainage, soil moisture, and the stability of landscapes. Over thousands of years, permafrost regions experience slow but persistent shifts in surface features, which may result in the formation of polygons, stripes, and terraces. These features often cover extensive areas and indicate long-term activity of freeze-thaw processes. The continuous interaction between ice, soil, and water shapes the terrain and affects the distribution of sediments, vegetation, and water bodies in frozen regions. In polar oceans, sea ice formation and melting follow seasonal and long-term rhythms. Sea ice grows during colder months and retreats during warmer months, influencing ocean currents and the distribution of marine sediments. Ice formation captures particles from the water, which are released when the ice melts, contributing to sediment deposition on the ocean floor. The formation and breakup of sea ice affect the habitats of marine organisms, as well as the flow of nutrients and the distribution of temperature in surface waters. Over thousands of years, these rhythms influence the structure of coastal and offshore environments, contributing to the long-term evolution of polar landscapes and ecosystems. Volcanic and geothermal activity interacts with freeze-thaw cycles in certain regions. Heat from underground sources can melt ice locally, creating streams of warm water that flow into frozen areas. The meltwater may refreeze downstream, affecting sediment transport and soil structure. Volcanic ash and other deposits can be incorporated into frozen layers, altering their composition and physical properties. Over extended periods, repeated freezing and thawing in combination with geothermal heat gradually modifies the terrain, producing unique features such as ice caves, subglacial streams, and thermal terraces. These features record the continuous interaction between heat, ice, water, and sediments over thousands of years. The rhythm of freezing and thawing is also evident in mountainous regions, where elevation and slope influence the distribution of ice and snow. Snowfields accumulate during colder months and compact into ice over time. Freeze-thaw cycles in rocks and soils at high altitudes contribute to rockfalls, landslides, and debris flows. Melting snow and ice generate runoff that flows into streams and rivers, shaping valleys and transporting sediments to lower areas. The ongoing cycles of freezing and thawing at different elevations create gradients in soil moisture, vegetation cover, and sediment movement. Over thousands of years, these processes influence the development of mountainous landscapes and the distribution of landforms at different heights. Sediments deposited by ice and meltwater reveal patterns of freeze-thaw activity over long periods. Glacial tills, formed from materials transported and deposited by glaciers, show evidence of repeated compaction, freezing, and melting. Outwash plains, composed of sediments carried by meltwater, record the gradual redistribution of materials as ice advances and retreats. Lakes and ponds in formerly glaciated areas often contain layered sediments that reflect alternating periods of ice cover and open water. These sediment layers provide a continuous record of freeze-thaw processes and allow scientists to trace the history of climate and environmental conditions over tens of thousands of years. In regions where seasonal freezing occurs, the topsoil experiences cycles of contraction and expansion that influence soil structure and nutrient availability. Organic matter becomes trapped in ice during freezing periods and is gradually released during thawing, contributing to soil fertility. Microbial activity fluctuates with the temperature and moisture conditions, affecting decomposition rates and nutrient cycling. Freeze-thaw cycles also affect the infiltration of water, as cracks and pores created by freezing allow water to penetrate deeply, while thawing may cause compaction that limits infiltration. Over thousands of years, these repeated processes shape the physical and chemical properties of soils, influencing vegetation growth, water retention, and landscape stability. The rhythm of freezing and thawing continues to operate in polar deserts, tundra regions, and cold steppe areas, where temperature extremes are common. The expansion and contraction of ice in rocks and soil contribute to slow but persistent changes in landforms, including the development of ridges, depressions, and polygonal ground. Seasonal snow and ice cover influence the timing and amount of water available to plants and animals, affecting ecological patterns over time. The distribution of sediments, rocks, and organic material in these regions reflects thousands of years of freeze-thaw activity, showing how persistent cycles shape both the physical environment and the ecosystems that inhabit it. Climate variations over thousands of years affect the rhythm of freezing and thawing. Longer periods of cold result in the expansion of ice sheets, glaciers, and permafrost, while warmer periods cause melting and redistribution of materials. Changes in atmospheric circulation, precipitation, and solar radiation influence the rate and extent of freeze-thaw cycles. Sediment cores from lakes, oceans, and permafrost regions record these variations, revealing sequences of cold and warm periods that have influenced landscapes, water systems, and biological activity. By studying these records, scientists can identify the timing, intensity, and impact of freeze-thaw cycles over thousands of years, as well as the ways in which landscapes respond to long-term temperature changes. Ice wedges, formed when water repeatedly freezes in soil cracks, provide a detailed record of past freeze-thaw activity. The size, shape, and orientation of ice wedges indicate the frequency and intensity of freezing events over time. Polygonal ground patterns created by ice wedges cover large areas in tundra and permafrost regions, showing evidence of ongoing activity over thousands of years. Sediments surrounding ice wedges contain organic material and particles transported by meltwater, offering additional insight into the dynamics of freeze-thaw processes. These features preserve a long-term record of environmental conditions, demonstrating the persistent influence of freezing and thawing on landscapes, soils, and ecosystems. The rhythm of freezing and thawing is evident in coastal regions affected by sea ice. Ice formation along shores captures sediments and moves rocks, while thawing releases them into tidal zones and shallow waters. Over thousands of years, this repeated movement shapes beaches, shorelines, and underwater sediments. Coastal erosion and deposition are influenced by the presence of ice, as frozen layers protect surfaces temporarily, while thawing allows sediments to be mobilized. The interaction between freezing, thawing, water flow, and sediments continues to reshape coastal landscapes gradually, leaving visible evidence in both surface features and sediment layers. Even in areas far from polar regions, freeze-thaw cycles influence the movement of water and sediments. In temperate regions, seasonal frost in soil creates small-scale changes that affect drainage, erosion, and soil structure. Cracks in frozen soil allow water to penetrate, and thawing may lead to minor landslides, sediment transport, or changes in river channels. Over thousands of years, these small-scale changes accumulate, contributing to the development of local landforms, drainage patterns, and soil distribution. Observing the effects of freeze-thaw cycles in different climates reveals the widespread impact of this natural rhythm on Earth's surface and the gradual shaping of landscapes over long periods of time. The interaction between freezing and thawing with vegetation, water, sediments, and ice creates complex patterns in landscapes. Ice formation lifts and moves soil and rocks, meltwater transports particles, vegetation stabilizes or destabilizes sediments, and repeated cycles of freezing and thawing leave permanent marks on the terrain. Over thousands of years, these processes operate continuously, shaping the land, influencing water distribution, and affecting the growth and distribution of plants and animals. Sediment layers, ice wedges, glacial deposits, and permafrost features all record the long history of freeze-thaw cycles, showing the slow but persistent rhythm that operates across different regions and climates. The rhythm of freezing and thawing influences underground water systems as well. When water infiltrates cracks in rocks and soil, freezing can block or redirect flow, while thawing allows water to move further into underground layers. Over time, this repeated process alters the distribution of water, nutrients, and sediments underground. Subterranean cavities, channels, and sediment deposits reflect the long-term effects of freezing and thawing, preserving evidence of past temperature fluctuations and water movement. Groundwater in permafrost regions is particularly affected, as ice-rich layers control the timing and availability of liquid water during thaw periods. The slow movement of glaciers over thousands of years demonstrates the cumulative effect of freezing and thawing. As ice accumulates, compresses, and moves downhill, rocks and sediments embedded in the ice are transported across long distances. The melting edges of glaciers release these materials, forming deposits that indicate the previous extent and movement of the ice. The interplay of ice formation, melting, water flow, and sediment transport reflects a continuous rhythm of freezing and thawing that shapes landscapes over long time scales. Glacial valleys, moraines, drumlins, and other landforms record this ongoing activity, illustrating the persistent influence of ice on Earth's surface. Polar oceans show similar rhythms as ice grows and melts seasonally and over longer periods. Sea ice captures particles and sediments from the water, releasing them when melting occurs. Currents and tides interact with ice formation and breakup, redistributing sediments and affecting habitats. Over thousands of years, these processes shape coastal shelves, underwater slopes, and shallow ocean regions. The movement of ice and water together reflects the long-term rhythm of freezing and thawing, affecting both physical and biological systems. Marine sediments preserve the record of these processes, showing patterns of ice formation, melting, and particle transport over extended periods. The rhythm of freezing and thawing can also be seen in human archaeological sites in cold regions. Structures, tools, and organic materials preserved in frozen soils reflect the impact of ice and thaw cycles. Repeated freezing can fracture rocks, lift stones, and displace materials, while thawing allows sediments to settle and water to flow. Over thousands of years, these cycles influence the preservation and distribution of archaeological evidence, providing information about the conditions in which past human communities lived. Observing the patterns of freezing and thawing helps researchers understand the long-term interaction between natural processes and human activity in frozen landscapes. The slow drift of continents during the Ice Age is a topic that involves understanding the movement of the Earth's land masses over millions of years and the environmental conditions that existed during periods of extensive glaciation. During the Ice Age, which consisted of multiple glacial and interglacial periods, the positions of continents were not fixed as they appear to be today. Instead, they moved gradually due to the processes of plate tectonics, which involve the shifting of the Earth's lithospheric plates over the more fluid asthenosphere beneath them. This movement, known as continental drift, happens at a very slow rate, often only a few centimeters each year, but over millions of years, it leads to significant changes in the positions and configurations of continents. The Ice Age refers to a period of time when global temperatures were much colder than today, and large portions of the Earth's surface were covered by ice sheets and glaciers. The most recent Ice Age is known as the Quaternary Glaciation, which began approximately 2,600,000 years ago. Within this period, there were multiple advances and retreats of ice sheets, called glacial and interglacial periods, which influenced sea levels, climate, and the distribution of plants, animals, and human populations. During these times, the slow drift of continents played a significant role in shaping the Earth's climate patterns, ocean currents, and the locations of ice coverage. The movement of continents during the Ice Age is part of a much larger geological process that has been ongoing for hundreds of millions of years. The theory of plate tectonics explains that the Earth's lithosphere is divided into several large and small plates that float on the semi-fluid asthenosphere beneath them. These plates carry continents and ocean basins and are constantly moving, although very slowly. The movement occurs due to forces such as mantle convection, ridge push, and slab pull. Over time, these movements cause continents to collide, pull apart, or slide past each other. During the Ice Age, the continents were not positioned exactly as they are today. For example, North America, Europe, and Asia were connected by land bridges during periods of lower sea levels caused by extensive glaciation, allowing species to migrate and influencing human populations. The drift of continents during the Ice Age also had a profound effect on the formation of mountains, valleys, and ocean basins. As continents moved, they sometimes collided, forming large mountain ranges such as the Himalayas, the Alps, and the Rockies. These mountains influenced local climates by affecting wind patterns and precipitation. They also served as barriers for ice sheets, guiding their movement and shaping the landscapes over which they traveled. Valleys, fjords, and basins were carved by both glacial movement and tectonic activity, creating complex topographies that would later affect ecosystems and human settlement patterns. The changing positions of continents also altered ocean currents, which in turn influenced global climates and the distribution of ice during glacial periods. The rate of continental drift is extremely slow but measurable. For example, modern measurements indicate that some continents move at rates between 2 and 10 centimeters per year, depending on the location and the forces acting on the tectonic plates. Over tens of thousands of years, these movements accumulate to produce noticeable shifts in the positions of continents. During the Ice Age, which lasted for millions of years, even these slow rates of movement resulted in significant changes in the configuration of the continents. These changes affected the flow of glaciers, the formation of ice sheets, and the locations of sea and land, which in turn influenced climate patterns, vegetation distribution, and the migration of animal and human populations. Continental drift during the Ice Age also interacted with other geological and environmental processes. For instance, the formation of large ice sheets added weight to the Earth's crust, causing it to deform and sink in some regions while uplifting in others. This process, known as isostatic adjustment, combined with tectonic movements to further modify the Earth's surface. As glaciers advanced and retreated, they transported sediments, carved landscapes, and shaped the topography of continents. The distribution of sediments, including moraines, drumlins, and glacial till, provides evidence of the combined effects of glacial activity and continental movement. The drifting continents affected not only the distribution of land masses, but also the depths and shapes of ocean basins, which influenced ocean circulation patterns and climate regulation. The positions of continents during the Ice Age were important for understanding the climate at the time. For example, the arrangement of North America, Europe, and Asia influenced the formation and expansion of ice sheets. Ice sheets were massive, sometimes covering millions of square kilometers. The Laurentide ice sheet in North America, the Fennoscandian ice sheet in Northern Europe, and the Siberian ice sheet in Asia expanded and contracted in response to changes in temperature, precipitation, and sea levels. The shape and position of the continents guided the flow of ice and determined where it accumulated or melted. Land bridges, such as the Bering Land Bridge connecting Asia and North America, were exposed during periods of low sea levels caused by ice accumulation, allowing migration of species, including early humans, between continents. The movement of continents during the Ice Age also affected ocean circulation, which is a key factor in regulating climate. The positions of continents determine the pathways of major ocean currents, which transport heat and nutrients across the globe. For example, the positioning of North and South America influenced the formation of the Gulf Stream, which carries warm water from the tropics toward the North Atlantic. Changes in ocean currents affected the distribution of heat, the formation of ice sheets, and regional climates. Continental drift altered the shape of ocean basins and the depth of seas, which also influenced the salinity, temperature, and circulation of ocean waters. These changes had long-term effects on the climate system and the distribution of ice during the Ice Age. The slow drift of continents also played a role in the evolution and migration of species. As continents moved and climates changed, habitats shifted, creating new ecological niches. Plants and animals adapted to these changes by migrating, evolving, or facing extinction. The movement of landmasses affected the connectivity of ecosystems, allowing species to spread across continents or become isolated in particular regions. For humans and other large mammals during the Ice Age, the drift of continents and associated changes in climate influenced migration patterns, access to resources, and survival strategies. Archaeological evidence shows that early humans moved across continents using land bridges and following animal herds, which were themselves affected by the changing positions of ice sheets and continents. Geological evidence for continental drift during the Ice Age comes from multiple sources. Paleomagnetic studies show the historical positions of continents by examining the alignment of magnetic minerals in rocks. Fossil evidence demonstrates the distribution of species across continents that were once connected. Sedimentary deposits and glacial landforms record the movement of ice and its interaction with the land. By combining these lines of evidence, scientists can reconstruct the positions of continents and the extent of ice coverage during the Ice Age. The slow but continuous movement of continents is evident in the alignment of mountain ranges, the matching of geological formations across continents, and the distribution of glacial deposits. The Ice Age spanned multiple cycles of glaciation and deglaciation. During each cycle, continents were slowly drifting, but the effects of ice sheet expansion and retreat were more immediate and visible. Ice sheets covered parts of North America, Europe, and Asia, while other regions remained ice-free. Sea levels fluctuated significantly due to the accumulation and melting of ice, sometimes falling by over 120 meters during glacial maxima. These fluctuations exposed continental shelves and land bridges, which facilitated migration and affected climate patterns. The ongoing drift of continents, although slow, contributed to the long-term shaping of the Earth's surface, influencing the location of oceans, mountains, and land masses over millions of years. The movement of continents also influenced volcanic and seismic activity during the Ice Age. As tectonic plates shifted, they caused earthquakes, formed mountain ranges, and created volcanic regions. Volcanic eruptions released gases into the atmosphere, which could influence climate on regional and global scales. Earthquakes reshaped the landscape and affected the flow of glaciers. The combination of tectonic activity, glaciation, and climate change interacted to produce complex patterns of land and ice distribution. Sedimentary basins formed as a result of both tectonic subsidence and glacial loading, creating areas where sediments accumulated and preserving evidence of past ice ages. The study of continental drift during the Ice Age requires the integration of multiple scientific disciplines, including geology, climatology, paleontology, and geophysics. By analyzing rock formations, fossils, ice cores, and sedimentary layers, scientists can reconstruct the positions of continents, the extent of ice sheets, and the interactions between land, ice, and oceans. Paleoclimate data, such as oxygen isotope ratios in marine sediments, provide information about past temperatures and ice volumes. The alignment of magnetic minerals in volcanic and sedimentary rocks indicates the historical movement of continents. Together, these data reveal a dynamic Earth where continents slowly moved, ice sheets expanded and retreated, and climates changed over millions of years. During the Ice Age, the continents were continuously shifting. North America gradually moved westward. Europe and Asia adjusted their positions in response to plate movements, and other continents such as Africa, South America, and Australia also drifted. These movements altered the shape and depth of ocean basins, affected climate patterns, and influenced the flow of glaciers. The slow drift of continents shaped the distribution of land and water, guided the formation of mountains and valleys, and affected the migration of species. The evidence of these movements is preserved in rocks, fossils, glacial deposits, and the alignment of geological structures. The interaction between continental drift and glaciation during the Ice Age created a constantly changing Earth. Ice sheets advanced and retreated over continents, causing erosion, sedimentation, and changes in topography. The positions of continents influenced the size and location of ice sheets, which in turn affected sea levels, ocean currents, and climate. As continents moved, mountain ranges formed or were uplifted, creating barriers for ice flow and influencing local climates. The movement of tectonic plates also caused earthquakes and volcanic activity, which further modified the landscape. Together, these processes resulted in a complex and dynamic Earth during the Ice Age, with continents slowly drifting while ice and climate continually reshaped the surface. Fossil evidence shows that species were affected by the combination of continental drift and glaciation. Many species migrated across land bridges exposed during periods of low sea level, while others became isolated in refugia, where ice did not reach. The drift of continents changed the connectivity of habitats, influencing the spread and evolution of plants, animals, and humans. Ice sheets covered large parts of North America, Europe, and Asia, and the retreat of these ice sheets created new habitats and altered the availability of resources. Sedimentary records, such as glacial till, moraines, and drumlins, preserve evidence of ice movement and the influence of drifting continents on landscapes. The formation of continents, ocean basins, and mountain ranges during the Ice Age was a slow process, but the effects were long-lasting. Continents drifted apart or collided over millions of years, creating changes in topography, ocean circulation, and climate. Glacial advances and retreats modified landscapes by carving valleys, depositing sediments, and reshaping coastlines. Ocean currents were affected by the positions of continents and the depth of seas, influencing climate patterns and the distribution of ice. The combined effects of continental drift and glaciation created a complex and evolving Earth during the Ice Age. The study of continental drift during the Ice Age continues to provide insights into Earth's geological history. Scientists use a variety of techniques, including paleomagnetism, fossil analysis, sedimentology, and geophysical measurements, to understand the movement of continents and the interactions between ice, land, and oceans. The slow drift of continents affected the formation of mountains, valleys, and ocean basins, influenced climate patterns, and shaped the distribution of species. Evidence from rocks, fossils, ice cores, and sediments allows scientists to reconstruct the positions of continents and the extent of ice coverage over millions of years, revealing a dynamic Earth that was constantly changing during the Ice Age. The movements of continents during the Ice Age also affected human populations. Early humans migrated across land bridges exposed by low sea levels, following animal herds and accessing new habitats. The drift of continents influenced the location of ice sheets, the availability of resources, and the formation of river systems. Archaeological evidence shows that humans adapted to these changing conditions by developing tools, clothing, and shelters suitable for cold climates. The slow movement of continents, combined with glacial advances and retreats, created a complex environment in which humans and other species had to navigate, survive, and adapt. The distribution of ice sheets and glaciers during the Ice Age was shaped by the slow drift of continents. As land masses shifted, the accumulation and flow of ice were influenced by topography, climate, and ocean currents. The expansion of ice sheets caused the lowering of sea levels, exposing continental shelves and land bridges, while the retreat of ice sheets led to the flooding of coastal areas. The positions of continents affected the direction of glacial movement and the formation of landforms such as valleys, fjords, and moraines. The continuous drift of continents created changes in the landscape that influenced ecosystems, climate, and the migration of species. The study of sediments and glacial deposits provides information about the interaction between continental drift and glaciation. Moraines, drumlins, eskers, and other glacial features indicate the movement of ice across continents, while the alignment of rock formations and magnetic minerals shows the historical movement of tectonic plates. Fossils found in these deposits reveal the distribution of species during the Ice Age and how continental drift influenced their habitats. Sedimentary layers in ocean basins record the effects of drifting continents on ocean circulation, climate, and ice sheet formation. The evidence from sediments and fossils allows scientists to reconstruct the dynamic Earth during the Ice Age and understand the slow drift of continents in relation to glaciation and climate change. The slow drift of continents continued throughout the Ice Age, with each movement contributing to changes in topography, climate, and ecosystems. North America, Europe, Asia, Africa, South America, Australia, and Antarctica all experienced shifts in their positions over millions of years. These shifts affected the formation of mountains, valleys, and ocean basins, influenced the flow of glaciers, and guided the migration of species. The ongoing movement of continents, combined with glacial advances and retreats, created a constantly evolving Earth where landscapes, climates, and ecosystems were continually modified over long periods of time. The interaction between continental drift and glaciation also influenced the chemical composition of oceans and the atmosphere. As continents moved, they exposed new rock surfaces to weathering, which released minerals and nutrients into rivers and oceans. Glacial erosion transported sediments to ocean basins, affecting the chemistry of seawater. Volcanic activity associated with tectonic movement released gases into the atmosphere, influencing climate and the carbon cycle. These processes contributed to changes in ocean salinity, temperature, and circulation, which in turn affected the growth and retreat of ice sheets. The continuous drift of continents was therefore linked to complex environmental and geological processes that shaped the Earth during the Ice Age. The movement of continents during the Ice Age can be traced through geological formations and fossil records. Mountain ranges, sedimentary basins, and volcanic rocks preserve evidence of tectonic activity, while fossils show the distribution of species across continents that were once connected. Glacial deposits indicate the extent and movement of ice sheets, and ocean sediments record changes in circulation and climate. By analyzing these records, scientists can reconstruct the slow drift of continents and the interactions between land, ice, and ocean over millions of years. The positions of continents during the Ice Age influenced climate, ecosystems, and the distribution of species, demonstrating the dynamic nature of the Earth's surface. The slow drift of continents during the Ice Age also affected the distribution of rivers and lakes. As land masses shifted, the courses of rivers changed, creating new drainage patterns and affecting the availability of fresh water. Lakes formed in depressions created by glacial activity and tectonic movement, providing habitats for aquatic species and influencing regional climates. The movement of continents altered the slopes and elevations of land surfaces, which in turn affected water flow, sediment transport, and the formation of deltas and floodplains. These changes had long-term impacts on ecosystems, human populations, and the overall landscape of continents during the Ice Age. The ongoing movement of continents interacted with glacial cycles to produce complex patterns of ice coverage and landscape modification. Ice sheets advanced over some regions while retreating from others, and the positions of continents influenced the distribution and flow of ice. Glacial erosion and deposition reshaped valleys, mountains, and plains, while tectonic activity created new features and modified existing ones. The combination of continental drift and glaciation produced dynamic landscapes that were constantly changing over tens of thousands and millions of years. Evidence from rocks, sediments, and fossils shows the cumulative effects of these processes on the Earth's surface during the Ice Age. The study of continental drift during the Ice Age continues to provide important insights into Earth's geological history. Scientists use methods such as paleomagnetism, fossil analysis, sedimentology, and geophysical measurements to reconstruct the movement of continents and the extent of ice coverage. The positions of continents affected the formation of mountains, valleys, and ocean basins, influenced climate and ocean circulation, and shaped the distribution of species. Glacial deposits, sedimentary layers, and fossil records preserve evidence of these processes, allowing scientists to understand the dynamic interactions between tectonic movements, ice sheets, and environmental conditions during the Ice Age. Continents continued to drift during the Ice Age at rates of a few centimeters per year, resulting in gradual but significant changes in the positions of land masses. These movements affected the flow and extent of glaciers, the formation of ice sheets, and the distribution of species. The interaction between continental drift, glaciation, and climate change created a constantly evolving Earth where landscapes, ecosystems, and climate patterns were continually modified. Evidence from rocks, sediments, fossils, and ice cores allows scientists to trace these movements and understand the processes that shaped the Earth during the Ice Age. The slow drift of continents, combined with glacial advances and retreats, influenced every aspect of the Earth's surface, from mountain formation to river courses, ocean circulation, and species migration. The continuous movement of continents during the Ice Age also affected sedimentation and erosion. As continents drifted, the slopes and elevations of landmasses changed, influencing the flow of rivers and glaciers. Sediments carried by ice and water were deposited in new locations, forming moraines, drumlins, and sedimentary basins. These deposits provide a record of the interactions between continental drift and glaciation, preserving evidence of ice movement, climate conditions, and tectonic activity. Over millions of years, the slow drift of continents combined with glacial processes to create complex landscapes that are still observable today. The drift of continents during the Ice Age influenced the formation of natural resources. Glacial and tectonic processes concentrated minerals, sediments, and soils in certain regions, affecting the distribution of resources such as coal, iron, and other geological materials. The movement of landmasses altered drainage patterns, soil composition, and the location of sedimentary basins, which in turn affected ecosystems and human activity. The slow drift of continents, combined with glacial advances and retreats, played a role in shaping the distribution of resources across the Earth. The end of the Ice Age was a process that took thousands of years, and it did not happen all at once. The Earth slowly began to warm, and as this warming continued, ice that had covered vast areas of land for many thousands of years began to melt. This melting happened in many different regions at different times, and it affected the land, the oceans, and the climate in ways that were very complex. During this period, the temperature of the Earth increased gradually, and this change in temperature caused glaciers, which are large sheets of ice, to shrink and retreat. In North America, Europe, and Asia, the massive ice sheets that had once stretched over millions of square kilometers slowly began to break apart and move back toward the polar regions. This process did not happen in a straight line, and there were times when the melting slowed down or temporarily stopped before continuing again. The melting ice released large amounts of fresh water into the oceans, and this affected ocean currents and weather patterns in ways that scientists today are still studying to understand in detail. As the ice began to melt, the landscapes that had been covered for tens of thousands of years by thick ice became visible. Mountains, valleys, and plains that had been buried under ice for so long were uncovered. Rivers and lakes formed as meltwater collected in low-lying areas, and some of these lakes grew to enormous sizes. One example of this is Lake Agassiz in North America, which formed from meltwater and covered vast areas of what are now parts of Canada and the northern United States. The formation of these lakes changed the way water flowed across the land and created new habitats for plants and animals. The retreat of ice also exposed soil that had been frozen for thousands of years, and as this soil thawed, it became available for plant life to grow. Grasses, shrubs, and eventually forests began to spread into areas that had previously been too cold and too icy to support life. The change in climate was gradual, but it was significant. Average temperatures increased by several degrees over thousands of years, and this allowed many species of animals and plants to move into new areas. Species that had been living in warmer southern regions slowly migrated northward as the ice melted and new habitats opened up. This movement of species also led to changes in ecosystems. Predators followed their prey into new areas, and herbivores found new sources of food. As forests expanded and grasslands developed, new ecological niches were created, supporting a greater diversity of life than had been possible during the height of the Ice Age. Animals such as mammoths, woolly rhinoceroses, and reindeer had to adapt to these changing conditions, and some populations moved to higher latitudes or higher elevations, where temperatures remained cooler for longer periods. Some species were able to survive and thrive in the changing environment, while others disappeared from certain regions. Human populations were also affected by the melting ice. Groups of humans that had lived in areas near the ice sheets had to adapt to new conditions. As the ice retreated, humans were able to move into areas that had previously been inaccessible. This migration allowed them to find new sources of food and resources, and it encouraged the development of new tools and hunting techniques. Humans followed the movements of animals that were important for their survival, and the changing landscape influenced the routes that they took and the places where they established temporary or permanent settlements. Archaeological evidence shows that humans began to inhabit regions that had been covered by ice for thousands of years, and they made use of rivers, lakes, and fertile soil that became available after the ice melted. The changing environment also influenced the patterns of human culture, including the development of new forms of art, symbolic objects, and ways of organizing communities. The melting of the ice also had an impact on the oceans. Large amounts of fresh water from melting glaciers entered the seas, raising sea levels gradually. This rise in sea levels flooded coastal areas and reshaped shorelines. Areas that had once been dry land became shallow seas, and islands were created as higher ground remained above the water. Rising sea levels affected the migration of human populations and the distribution of animals and plants. For example, the flooding of land bridges, such as the one that had connected Asia and North America, changed migration routes for both humans and animals. The melting ice also influenced ocean currents, which in turn affected climate patterns around the world. Changes in the movement of ocean water helped redistribute heat across the planet and contributed to regional changes in temperature and precipitation. As the ice melted, new landforms were created. Glacial valleys, moraines, and drumlins appeared as the ice retreated and left behind rocks, soil, and sediment that had been carried along by moving glaciers. These features altered the drainage patterns of rivers and the formation of lakes. Glacial meltwater carved new channels and reshaped the landscape in ways that were sometimes dramatic. In addition, the melting ice caused the land to slowly rise after being compressed by the weight of the glaciers, a process called isostatic rebound. This rise continued for thousands of years after the ice had melted and changed the relative elevation of coastal areas and inland regions. The effects of glacial retreat can still be seen in many parts of the world today, in areas such as Scandinavia, Canada, and the northern United States, where the land is still gradually adjusting to the loss of ice from the last ice age. The retreat of ice was not uniform, and it happened at different speeds in different regions. Some areas experienced faster melting because of local climate conditions, while other areas remained covered by ice for longer periods. Factors such as latitude, elevation, and proximity to the ocean influenced how quickly the ice disappeared. In addition, volcanic activity, changes in the amount of sunlight reaching the Earth, and variations in the Earth's orbit played a role in the timing and pace of ice melting. The combination of these factors led to a complex pattern of glacial retreat, with some regions opening up to plant and animal life, while others remained frozen. Scientists use evidence from ice cores, sediment layers, and fossil records to study these patterns and to understand the timing and sequence of events that occurred during the end of the Ice Age. The melting of the ice sheets also affected the climate on a global scale. As ice melted, it reflected less sunlight, which contributed to further warming. This feedback loop accelerated the melting process and led to changes in weather patterns. Precipitation increased in some areas, creating wetter conditions, while other regions became drier. The distribution of forests, grasslands, and deserts changed as a result of these climatic shifts. These changes in vegetation influenced the types of animals that could survive in different regions, and they also affected human societies that depended on plants and animals for food. Over thousands of years, the combination of melting ice, changing climates, and rising sea levels reshaped the Earth's surface and created the conditions for the world as it exists today. During this period, glaciers in many parts of the world, including Europe and North America, receded slowly. In Europe, ice that had once covered much of Scandinavia and parts of the British Isles melted gradually, exposing fertile valleys and plains. In North America, the Laurentide ice sheet, which had covered large parts of Canada and the northern United States, retreated northward, revealing vast areas of land that had been buried under ice for tens of thousands of years. This newly exposed land provided opportunities for plant and animal life to expand into areas that had previously been uninhabitable. Vegetation such as tundra grasses and shrubs colonized these regions first, followed by forests composed of birch, pine, and other tree species. Animals migrated into these areas in search of food, and humans followed them, taking advantage of the new resources that became available as the ice melted. The process of melting ice was not smooth and continuous. There were periods when the climate cooled temporarily, slowing down the retreat of glaciers, or even causing them to advance slightly. These interruptions were often caused by natural variations in the Earth's climate system, such as volcanic eruptions that temporarily reduced the amount of sunlight reaching the Earth, or changes in ocean circulation patterns. Despite these interruptions, the overall trend was toward warming, and over thousands of years, the ice sheets continued to shrink. The gradual melting of glaciers created rivers and streams that flowed from the ice sheets toward the oceans. These rivers carried sediment and nutrients that helped fertilize soils in downstream areas, supporting the growth of plants and the development of ecosystems. The changes in vegetation during the melting of the ice also influenced animal populations. Herbivores were able to find more food as grasslands expanded, and predators followed their prey into newly available territories. Some species moved long distances to track changing habitats, while others adapted to new food sources and environmental conditions. The melting ice created a mosaic of habitats that supported a wide variety of species, and the interactions between plants, animals, and humans shaped the ecological landscape in ways that continued to evolve over thousands of years. Humans adapted their hunting strategies and developed new tools to take advantage of the resources provided by the changing environment. This adaptation was crucial for their survival as they moved into areas that had been previously covered by ice. The release of fresh water from melting ice sheets had a significant impact on ocean levels and currents. As glaciers melted, the additional water raised global sea levels, flooding low-lying coastal areas and creating new shorelines. In some regions, large freshwater lakes formed, which eventually drained into the oceans, contributing further to sea level rise. The changes in sea level altered the connections between continents and islands, affecting migration routes for both humans and animals. Ocean currents, which play a critical role in distributing heat around the planet, were affected by the influx of fresh water, leading to changes in temperature and precipitation patterns in different regions. These changes influenced the distribution of vegetation, the movements of animals, and the development of human societies along coastlines and river valleys. The process of ice melting also had long-term geological effects. As glaciers retreated, they left behind deposits of rocks, gravel, and sand, creating features such as moraines, drumlins, and eskers. These deposits shaped the topography of the land and influenced the flow of rivers and the formation of lakes. In addition, the removal of the weight of the ice allowed the land to rise, a process called isostatic adjustment, which continues in some areas to this day. The combination of melting ice, rising land, and sediment deposition created landscapes that were dynamic and constantly changing over thousands of years. This ongoing transformation provided new opportunities for ecosystems to develop and for humans to settle in areas that had been uninhabitable during the height of the Ice Age.